alignment. Don't think there's any question. Merrill Ritter showed nice long-term studies demonstrating and in many, many other centers, by the way, any degree of varus on the tibia seems to be associated with an increased rate of failure. So there's some debate as to the exact target, but there's no question we want to avoid some of these malalignments. The way I see a robot in 2019 and 2020 is really just an evolution of this instrumentation. We have some wonderful videos at Insall, Scott Kelly, of John Insall holding that bar up and lining it up with the tiles in the side of the room. And we've obviously moved on from that, and I think this is just a next step. We've seen an evolution in the prostheses. We've gone from 2 femoral sizes up to 38 femoral sizes I have today, with multiple different iterations and combinations that I can use. So my thought process and why I was saying that the soft tissue balance may not be as important is if you put the component in the right position. I'm not suggesting you don't have to balance the soft tissues, but you have to do it far less so than Dr. Insall did when he had only 2 sizes. So I think when we put them in accurately, what I've found is that we have less need for large releases. So what is a robot? It's an interesting history. It was a guy between the 2 wars. It's a Czech word, and it was used in a play, actually, and it described forced labor or repeated boring drudgery, which I always thought represented my position as a junior attending at ISK for my first 10 years. So my active robotic experience, this is an iterative use of this system. This system's been around. It was designed by Bill Barger in the early 1990s with Hatball and IBM. And so this is a milling technology. It's actually got a lot of proprietary technology around the CT scan, and that's really important because you can only do something accurately if you can measure it accurately initially. And I'll show you some of our accuracy data. So they've used this for more than 30,000 cases in Europe and Asia, but we have not used it in the United States. Clinical outcomes have been published from other centers. Here are a few of them with good survivorship and about 25 minutes longer surgical time, which is about what we got down to in our study. So I was one of 5 surgeons involved in this multi-center IDE study in the United States, and I should say that IDE is an investigational device exemption in the United States. The Food and Drug Administration allows you to do this and make it similar to previous systems. So it involves 3 steps: CT scan, planning, and then going into the OR. And each of these is very important because you cannot go back, and you can't change the plan, and you can't change the execution in the OR. So you've got to make sure you've got a good CT scan and you've got a good plan. So here's the CT scan and segmentation. This is the way it arrives in my office. And these are screenshots taken from my computer. It initially required a lot of individual engineer evaluation, but their algorithms are a lot tighter now, so there's less sweat and tears that go into it. You have to choose the landmarks. Very interesting. You start to really look at some of this bony anatomy around the knee when you've got to choose the positions of your epicondyles. You then plan the femur, and you can align this anatomically, mechanically. You can rotate it wherever you'd like, take any different depth of resection, change your sizes, anything you want. And the femoral rotation options, as you can see here, which is interesting to fiddle with whether the posterior condylar axis is actually parallel with the epicondylar axis. So you get to learn a little bit about the anatomy and where we're putting these components. You've got long leg alignment options, as I mentioned, and you can see the completed plan that it gives you here. You then take that into the OR, and here's quickly, this is only 1 minute, but this is one of my cases. I always cut the patella first, I ream it, and then just complete the cut. It gives me better space. These are the fixation pins that I was just putting in. Those are the registration pins and markers. There are a lot of pins that go into bone. You actually secure the robot right to the patient, so they're secured to the leg. And then there's special motion monitors that I'm putting in there to make sure that there's no motion with respect to the robot. You then register. This is a very painful thing for most surgeons to do, myself included. But you have to go through and register all these points. I've argued with the engineers about making this faster and more user-friendly. Then you press the button, you stand back, and you use suction and a retractor. The robot comes in and it burrs. So it always does the femur first. You can see it going along here. And this has sub-millimeter accuracy that I'll show you. Here it is doing the tibia as well. And it's about this exciting when you're in the OR, by the way. Pretty boring motion. And then we complete it in a standard fashion. But you can really see those bony surfaces are very, very accurate, very, very smooth. There's no teeter-tottering. These are not resonant cuts. I still cement, although an argument could be made with some of these surfaces.
Very fast.
So our preliminary results, no major complications. I think it's important to evaluate a new tool when you're bringing it into the OR. 5 AEs in 5 patients. The only one I would point out is leaving a metal pin behind. Thankfully, I did not do that, but one of my colleagues did. So you learn to count and make sure that things were out of the wound. We did full-length CT scans at 3 months. This is actually a requirement of the FDA, so, but it gave us some really neat data. And we then overlapped where our cuts were, where our plan was with the preoperative and postoperative CT scan. And what it showed us, and this is, I will point out, anytime you're going to use a new robot, you need to know the technology. And you should go and ask the company, what is your 3-dimensional sub-millimeter accuracy in terms of position and rotation? And I think you might be surprised to find that although they'll publish studies on how great the outcomes are and how people go home faster, there's very little published on their accuracy. And so this study we did publish 0.2, 0.1 millimeters of accuracy. Incredibly accurate tool. The femoral component, it shows the size every time. The tibial component, when the surgeon is free to change in the OR, we actually switched a little bit. I was less interested in templating the tibia accurately, but it picked the femoral component perfectly. And you can understand as a surgeon why that's very important, as it's very hard to go back on that step. Average surgical time went down pretty significantly. The first few cases took us a little longer, and here were my surgical times, much more linear. I'm someone who likes to make sure I master the technique and then get quicker and quicker. The clinical function, I'm not here to tell you that a robot's making the Knee Society scores or SF12 scores better, but they did all improve significantly. We did show, and I showed this yesterday, with another robotic system, and I think this is perhaps one of the really nice things a robot does, is it brings the lower volume surgeon up to the level of the high volume surgeon. The benefits to robotics may also include less surgeon and surgical team fatigue, although I still think collecting those points tires me out more than using the saw blade. Companies see this as increasing their sales, more marketing, lower inventory costs, because they knew exactly what size we were going to use at the beginning of the case. So do I think it's coming to a hospital near you? My answer is it depends. It depends on your volume at your hospital, your environment, and how comfortable you are with new technology. In conclusion, these are early clinical results. It is a very accurate, very reproducible cutting tool. We didn't see any new robotic-specific complications. In the future, I think it might allow us to improve the component alignment, the bony interfaces, and perhaps the components. You can imagine a day where a tibial component isn't designed so an oscillating saw puts it in as a flat plate. And it sort of opens up your imagination to some of these future designs and hopefully eventually improving our clinical outcomes. Thanks.